Alright, hope you're ready for session 2. Today we're going to be talking about thermal expansion and the relationship between PV and now temperature as well. So you already should know the relationship between pressure and volume. Now we want to introduce temperature as well. Okay, starting off with a reminder. So the hotter, we learned last time, the hotter the temperature, the faster the particles will move, meaning the average kinetic energy of the particles is higher when the temperature is higher. So you already know that when the temperature rises, the kinetic energy of particles also rises. So they start to move faster. So now building on that, as they start to move faster, the distance between them will start to increase. They will start to move a bit faster, and so they will start to expand. So that's something that you should know, is that it's called thermal expansion. So because of the heat, the shape, the size of whatever material we're dealing with, whatever state of matter it's in, they will all expand when you add temperature to them.
Stop. No, you can never add temperature, you only add heat. I apologize.
This is an example showing that the number of atoms hasn't changed, it just, the distance between them has increased. That's important to note, is that the volume has increased. The mass will still be the same. It's still the same number of atoms. The density will reduce, right? This is how they are in a cooler temperature. If you increase the temperature, they will start to move more. If they move more, they will expand. They will take up more space. Another idea for thermal expansion: the more material you have, the more the amount of expansion, because the distance between an atom and an atom is going to increase. So the more atoms you have, the more the increase will be. It will add up to more increase, basically. It's similar to when saying, back to Hooke's law, if the original length is higher, for the same amount of force, the extension will be more. So this is, for example, 1 meter of an object. So this is an example. Every material will be different. If, say, we say every 1 meter of a certain material, whatever this material you want to say it is, will increase by 20 centimeters with every 20 Celsius increase in temperature. So say we were at 100 degrees, it was 1 meter long, and then we increased the temperature to 120 Celsius. This is the new length. If you started off with twice the length, you're going to end up with twice the extension. Now it's also worth mentioning that the increase will happen in all 3 dimensions. So not just in 1 dimension, but we're only focusing on 1 dimension. If it's in 3 dimensions, it's going to increase in a 3-dimensional form. You can open the Word document again and see there's a part on thermal expansion if you wanted a more wordy explanation. So here it's saying that if a solid is heated, its molecules gain kinetic energy and therefore they will vibrate more vigorously, and the spaces that they occupy will increase. And when it's cooled, the reverse happens. It's also important to note that different materials expand differently than others, so it depends on the material. And the expansion in length increases when the original length increases. So if you have more of the original length, you'll have more expansion. And obviously, the more you increase the temperature, the more the expansion. And it also depends on the type of the material. Okay, the expansion will happen in a 3-dimensional form.
If you look at the top 2 figures on page 108, you will see that here every 1 centimeter of this material before adding the heat will expand by 0.15 centimeters if you measure them. So every 2 centimeters will expand by 0.3, and every 4 will expand by 0.6. So if you measure the before and after of different lengths, original lengths, you'll see that the extension is different. So it's more if the original length was more, but the percentage of expansion is the same. But if it's percentage-wise, the more you start off with, the more you... So when you start off with an original length of 2, the extension will be 0.3, and start off with an original length of 4, you end up with extension of 0.6. So the more original length you have, the more the extension.
You can also see from page 108 that different materials expand differently than other materials. So this is an example, a real-life example of the increase in length of a 1 meter bar for a 100 degrees Celsius rise in temperature. So you can see how different materials expand differently. That also helps with engineers in determining which material to use. For which application? So this is an example of if you compare two different materials, you're heating it by the same amount, but the expansion is going to be different. It depends on the forces of the molecules. Which type of atom or which type of material are you using? They would have different forces, so the expansion will also be different because the expansion depends on the forces. Now, I've had this question asked by a student earlier this year, and I told him to wait till we reach chapter 5. Shout out to Sanad. So he asked, some glasses can break when hot water is poured into them. Can you think of why? So some people are scared of using certain glassware into the oven. You have to use what's called a Pyrex. Pyrex glass is modified glass. It's made in a different way so that it wouldn't break, because normal glass would break. Why would it break if you heat it up from a certain point? So if you have a glass of water, empty glass, and you pour in hot water, what's going to happen? So what would happen is the glass will heat up from the inside a lot more than what's happening on the outside. So it's going to want to expand from the inside out. The outside part of the glass does not want to expand as much as the inside. So you're going to have to, the inside is going to want to force the outside to expand. If it's weak enough, if the bonds are weak enough, then the glass will shatter or break. And it also depends if the temperature difference is enough for that to happen. So if the glass was really, really cold before you poured in the really, really boiling hot water, then it's more likely to break than if it was at room temperature and the water that you're adding is not as hot as 100 Celsius. Right, now one good use of thermal expansion is what is called a bimetal strip. So as you can see here, it's basically a rod made of two rods welded together. Welded as in melted onto each other. The idea of a bimetal strip is that both rods would have different thermal expansions. The reason for that is, as the temperature around them increase, one of the rods will want to expand more than the other rod, causing a bend. So we want that bend to occur. So the brass here extends more than the steel when it's heated, and then it contracts more when it's colder. It will allow the bimetal strip to bend however way we want it, depending on the temperature. Going back to this document, scroll down, you'll see the use of the bimetal strip. So if you see here, that's why we use a bimetal strip. You will take electricity next year, but I'm sure you all know by now that electricity has to move from one point to another. You have to have a circuit, a closed circuit for something to happen. So this is a bimetal strip. If the temperature increases too much, it's going to bend down. So you can connecting the wires together and causing the alarm bell to go off. So that's how a temperature-dependent alarm can be used. You can argue that it's safer than, say, an electric alarm bell waiting for someone to press a button. This is actually depends on the temperature. If the temperature does rise, the strip will bend down and it will cause the alarm bell to go off. So that's a useful form of thermal expansion. But the idea is not all thermal expansion is good, and we just have to make sure that we understand thermal expansion, and so when we're using it in real life that we're careful for accidents not to happen. So examples of that is train tracks, even though we know that we don't have many train tracks, but as they heat up in the summer, they might buckle. So you usually add this bit that allows it to extend and compress easily without having it buckle or stop working. And also in bridges, so I don't know if you've ever noticed, if you ever went on any bridge, so the example I've been using for years is when you go over the 8th circle in Amman, you're going to hear the tires go over certain metal strips that you're going to see. I think I've counted them, I think there were 8 of them in the same bridge. So you're going to feel the car going, so what is the car going over? And it's the answer to that is thermal expansion joints. So they do this so that the bridges in winter, if they contract too much, they don't get ruined. And in the summer, they don't expand too much and they don't have space for the expansion that they also break. So obviously, if they break, they're going to kill lots of people. So engineers are responsible to know about thermal expansion and to take that into consideration in their design. Another thing is transmission lines or electrical lines. You have to make sure that, you have to know when you're building it, whether it's in the summer or in the winter. If you build it in the summer and you make it really tight, in the winter it's going to become shorter and it might cut the electricity. Same with winter. If you make it sag a lot in winter, it's going to sag even more in the summer, and it might reach the ground, and it might be not safe for people to walk around there. It might be more risky, so it might increase the risk. So you have to take that into consideration when designing certain things that depend on thermal expansion. Okay, so the idea as well is that liquids will expand more than solids in the same increase in temperature, and gases will expand even more than liquids. Can you think of a reason why? So why do you think that liquids will expand more than solids and that gases will expand even more than liquids? You can read more about that in page 111 in the last paragraph. So it's because the distances are already further apart, but mainly it's because the forces are weaker. So the same increase in temperature, the same increase in kinetic energy, but the forces forcing them to stay in their spot are weaker, so they are more likely to expand into a larger size. So liquids will expand even more than solids, and gases will expand even a lot more than liquids. If you look at page 111, it tells you here that water expands 7 times as much as steel for the same temperature increase, same rise in temperature, and air expands 16 times as much as water. So you can see that water is even more likely to expand than solids, than steel, and air will expand a lot more than water for the same rise in temperature. Let's talk a bit about thermal expansion of liquids. So I don't know if you're aware of this. I think most of you are aware of a thermometer, which we will be talking more about and how it actually works in the next session. You have the same number of atoms in the thermometer. They just expand. So as you can see, as the temperature increases, the distances between them will increase, and so it will rise up, and we can read the temperature then and determine it and be able to read what temperature we're at right now. This also shows you that the liquid has expanded. If it's expanding more and it's moving more, it will allow the mercury to rise even more. So more about that next session. Now, there's one thing that you need to know. Not all liquids will expand with temperature. The only exception to that rule is water. You don't need to know why. There's a video that I took this screenshot from on YouTube that talks about hydrogen bonds. You don't need to know the exact chemistry of it. You just need to know that water is the only exception, because we all know that ice floats, right? Whereas with any other liquid or any other material, the solid of that material will always sink. So water is the only exception. The reason for that is, what you need to know is that when water is a liquid, all the molecules are going to be sliding over each other. Whereas when it starts to freeze, it will start to want to form into a really nice crystal-like structure that requires more distances. More of that, page 109, if you want to read a bit more about that. Okay, so now let's go to gases and the thermal expansion of gases. So you already know the relationship between P and V when temperature is constant. Now you need to know the relationship between P and T when V is constant, and V and T when P is constant. So that's pressure and temperature when volume is constant, and volume and temperature when pressure is constant. If we have a container with a piston, and let's pretend that this piston will not move and that it's sealed in place, and that we have gas particles inside that are moving randomly. So if you apply heat here, so if you add a Bunsen burner here, you allow heat to be transferred into the gas particles. So when heat is applied, the kinetic energy of the gas particles will increase. So what would happen when the kinetic energy of the particles increase? The number of bombardments on the wall will increase, because if you're moving in a faster pace, you're more likely to hit the wall, and it's going to happen more often. So if it's happening more often, the number of bombardments is increasing, therefore the pressure will increase. In case you forgot the relationship between bombardments and pressure, I thought I'd explain it a bit further here. So you should know that pressure is the total force exerted on all the walls in a second over the area of these walls. So to calculate the force, you need the sum of all the tiny forces. These tiny forces are caused by the bombardment of each particle onto the wall. So each particle, when it bombards the wall, it will cause a tiny force. The sum of all of these forces will give you the total force that you need to calculate the pressure. Every particle will lose some of its momentum when it bombards with the wall of the container. And if you remember from earlier, the change in momentum is impulse, which is force times time. So if a particle hits a wall and its momentum changes, obviously because if it has a certain velocity going that way, it's going to hit that wall and its velocity will change into the other direction. If the direction changed, that means its velocity has changed. That means its momentum has changed. So, change in momentum is force times time. So say we're calculating all the change in momentum of all the particles in 1 second. You can then calculate the force that you need. And then if you have area, you can then calculate the pressure. So the more number of bombardments that are happening every second, the higher the pressure will be. So the more the bombardments, the more the force, the more the pressure. So going back here, the idea is when temperature rises, if V is constant, pressure will also rise. That's what you need to know. So the relationship between T and P is directly proportional. Now what would happen if you allow the piston to move, if you make it movable? So what's going to happen is the pressure is not allowed to rise. If the pressure increases and the force increases, the force will move the piston up. If you increase the volume, as you remember from before, increasing the volume will reduce the pressure. So another way of thinking about it is that pressure is increasing as temperature increases, but we're saying the pressure is constant. So the pressure is constant, that means the volume has to increase to let the pressure, to not allow the pressure to increase. So if you want to decrease the pressure and drive it back to normal, you have to increase the volume. So for that to happen, the piston will move upward. So we want the number of bombardments in every centimeter cubed to be constant, and we want the pressure to stay the same. So if you want that to happen, you also increase the area. As you know, if you increase the area, you reduce the pressure. So the idea here is that both pressure and volume are both directly proportional to T.
So now we know that whenever T increases, V also increases. So what you can say about this relationship is that T is directly proportional to V. As you remember from before, with P and V, we used to say that whenever pressure increases, volume has to decrease, and vice versa. We used to say that P is indirectly proportional to V. And then we also used to say that PV is constant, because whenever P increases, V has to decrease, and then whenever P decreases, V has to increase. Similarly, we can now say that V over T is now constant, because whenever T increases, V has to increase, and whenever T decreases, V has to decrease. And now, with T and P, whenever T increases, P increases as well. So we can say that T is directly proportional to P, and we can also say that P over T is constant. So whenever T increases, P has to increase. Whenever T decreases, P has to decrease. Now, to join P, V, and T onto one equation, what we can do is we know that PV has to be constant, we know that V over T has to be constant, and we know that P over T has to be constant. So we can combine all of these three together to create one constant, which is PV over T has to be constant. And now, whenever we say that V has to be constant, whenever T increases, P has to increase. And whenever we say P is constant, and whenever T decreases, V has to decrease. And vice versa. And also what we can say is when temperature is constant, whenever P increases, V has to decrease. You don't have to know when one of the three is not constant. That's for later years.
Now we are done with classes 5.04 and 5.05 from the chapter. So from page 108 to page 111. You can now attempt to do questions page 109, 111. Next session we will be talking about how to measure temperature. And it was in a hub. So so it will allow the connecting the rods together. So they usually add this part that allows it to extract it. That allows it to extend. That allows it to That allows it to extend and compress. Okay. But basically you have the same number of atoms in a whereas when they form into a liquid, the kinetic energy of the gas particles will, so hang on, I forgot my book downstairs.